Um, the chapter 6, normal probability distribution, section 6.4, the central limit theorem. So, the central limit theorem, what happens is when we try to solve real life problems, most of the time the distribution of the data is not normal. So, in that case, we cannot apply section 6.1 and section 6.2 to solve the problem. So, what we do, we can now use central limit theorem, which states for all samples of the same size n, with n is greater than 30. So let's say you have a population which is not normally distributed data. If you take the sample from that population with the sample size greater than 30, so you make the sample, let's say sample 1, sample 2, sample 3, all of them have the size, the fixed size, which is greater than 30. Now we can find average of each of these, not the average, sorry about that, mean of each of these samples, as you can see here, x1 bar, x2 bar, and x3 bar. Now this mean of these samples, they behave like a normal distribution. And and now you try to find the mean of all these sample mean, that would be equal to the mean of the population. So mean of all these sample means is equal to the mean of the population, and then standard deviation would be equal to the standard deviation divided by square root of n. That would be the standard deviation of this data, not the original data. Okay, so that's the central limit theorem. So we can approximate any data by using central limit theorem. We can approximate that data by finding the by taking the sample with the sample size greater than 30 and changing it to the uh, with the same mean of the population, and standard deviation would be a little bit different. So that would be now normally distributed data. Okay, so population has a mean mu and then standard deviation sigma here. Sample, now choose the simple random samples, all of the size n, the fixed size n, and that's greater than 30. By doing that, now find out the mean of all those sample means. That would be equal to the population mean, and then standard deviation of that sample mean, that would be equal to the standard deviation of the population divided by square root of n. And this is the formula, g score formula for that sample mean. Okay, so that's the conversion formula. The distribution, keep in mind, for that, these three things, whatever conversion we're doing, that's only possible if population has a normal distribution, or the value of n, which is sample size, is greater than 30. So if original population has normal distribution, this is already, we can do it. Or if the sample size is greater than 30. If the sample size is less than 30, then we cannot use that criteria, this formula. Okay, so whenever population is not normally distributed and the sample size is less than 30, then we cannot use this central limit theorem. So central limit theorem cannot be used for this situation. Okay, so you always have to check when we try to solve practical problems, either the original population is normally distributed, or if it's not, then sample size is greater than 30. That's a requirement we need to check. Okay, and for individual data, it's always, there is a g score we can calculate, and we can change the data into uh, uh, the standard normal distribution. When working with an individual value from a normally distributed population, you have to use this. But keep in mind, the population has to be normally distributed. That's from section 6.2. Okay, uh, if we are using mean from a sample, then this is the g score we are going to take, and then our mean would be same as the population and the standard deviation would be that one. So one more time, if we are talking about the sample where the sample is normal, the population is originally population is normally distributed, or the sample size is greater than 30, then these are the formula we have to use here. This notation is also called a standard error of the mean. Okay, so identifying significant results with probability, a real event rule for inferential statistics. If under a given assumption the probability of particular observed, this is the significance rule, where we can find the significantly some values which is significantly less than or significantly greater than values like before. Okay, one more thing I would like to mention here in this section: if you have a finite population, then and if we're taking the sample size greater than 5% of the original size, then always, if you have a standard deviation for the samples, then multiply that by this number. That's called finite population correction. So let's look at some examples from this section. Some examples. uh, 6.4. Okay, I'm going to check this is quick check. Fill in the blank. The blank tells us that population with any distribution, the distribution of the sample means approaches the normal distribution as the sample size increases. What tells you that? That's the central limit theorem. The standard deviation of the distribution of sample means is, this is the standard deviation of the distribution of the sample means. That's the formula. Which of the following is not a conclusion of the central limit theorem? The distribution of the sample data will approach a normal distribution as sample size increases. The distribution of the sample means x bar will, as the sample size increases, approach its normal distribution. The mean of all sample means is the population mean mu. The standard deviation of all sample means is the population standard deviation divided by the square root of the sample. So this is right. The distribution of the sample data, this is not right. The distribution of the sample data will approach normal distribution. No, that's not right. That's not part of the central limit theorem. Uh, a researcher collects a simple random sample of a grade point average. So remember, the data is grade point average of statistics students, and she calculates the mean of this sample. Under what condition can that sample mean be treated as a value from population having a normal distribution? So the researcher collects more than 30 samples. If the population of a statistics student has a normal distribution, this is for sure. Uh, if the population of a statistics student, no, not the student, it's the grade point average. The sample has more than 30 grade point average. If the population of grade point average has a normal distribution, and yeah, so then in that case we can apply a central limit theorem. Okay, here's the thing: assume that amounts of weight that male college students gain during their freshman year are normally distributed, the mean 1.1 kg and standard deviation 5.1 kg. If one male college student is randomly selected, keep in mind this is normally distributed, so we can use that normally distributed calculator. So go to the stat calculator and then normal distributed calculator. In this case, the average, the mean is 1.1, and then standard deviation is 5.1 kg. If one person select randomly, what is the chance that person weight is between 0 kg to 3 kg? That can be calculated by using this normal calculator. So what is the area under the curve from 0 to 3? That's 0.2306. 0.2306. That's the probability if you pick 1% randomly. Now, instead of picking 1% randomly, if you pick 25 male college students are randomly selected, find the probability that their mean weight during the freshman year is between 0 to 3 kg. Keep in mind, this is the sample. So whenever you pick the sample, your mean of the sample would be the same as the population, but the standard deviation is the standard deviation of the population divided by square root of the sample size. In this case, if you look at the problem, the sample size, the mean is 1.1, the standard deviation is 5.1 divided by the square root of the sample size. In this case, sample size is 25. So square root of 25 is 5. So I want to find out, if we take the sample of 25, what is the chances of, you know, their their mean, the mean weight of that 25 student would be 0 to 3 kg. And that's 0.8283. So 8283. So that's the chance. 8283, their mean would be in between 0 to 3 kg. Okay, that's part B. Part C, why can the normal distribution be used in part B? We can use the normal distribution here because the original population is normally distributed. So that's the requirement. The central limit theorem says if the original population is normally distributed, then any sample would be normally distributed. That's the one requirement. Or if the sample size is greater than 30, then that would be also normally distributed. In this case, the sample size is less than 30, but the original population is normally distributed. So, what is that? Since the original population has normal distribution, we can use the normal distribution for that. Let me go to another problem. A water taxi carries passengers from Harvard to another. Assume that weights of the passengers are normally distributed. So remember, the population is normally distributed already, with the mean 195 pounds and standard deviation is 42 pounds. The water taxi has a state capacity of 25 passengers. And then water taxi was rated for a load limit of 3,750 pounds. Given that the water taxi was rated for the load 3,750, what is the maximum mean weight of the passenger if the water taxi is filled to the state capacity of 25? So keep in mind, um, if you have maximum capacity 3,750, and if there are 25 passengers, then mean weight would be divide that number by 25, and that's 150. That's the maximum mean we can take. And if the water taxi is filled with 25 randomly selected passenger, what is the probability that their mean weight exceed the value from part A? So we want to find out using this normally distribute normal calculator, because the original population is normal. So the mean is, we have given in this problem, the mean is 195 pound, 195 pounds, and then standard deviation is 42. Now we would like to find out if water taxi is filled with 25. This is the sample related problem. Whenever that happens, the standard deviation has to divide by the square root of 25, which is 5. In this case, n is 25. We are using this formula. So that would be 42 divided by 5. And we want to find out what is the probability that their mean weight exceed the value from A. So that is 150. So this is not between, that's a standard. This is greater than 150. What is the probability that the mean weight is greater than 150? That's 100% of the chance. If you round it to the 4 decimal place, it's 100% chance. Okay. If the weight assumption were revised so that the new capacity become 20 passenger, and then water taxi is filled with 20 randomly selected passenger, what is the probability that their maximum mean weight exceed 187.5? So keep in mind, before it was 25, so you had to divide that by square root of 25, but this time it's a 20, so square root, the formula is as this is how you have to type SQRT, that means square root of 20, And now we would like to find out what is the probability that this value, the mean value, is greater than 187.5. 187.5. So with this mean and this standard deviation, what is the probability that mean weight would be greater than this? That's 0.7877. If you round it to the 4 decimal place, 0.7877. Let me double check. 0.7877. Okay, so that's the probability. Here it was 100%, here it's a 78.77%. Is the new capacity of 20 passengers safe? Still this is high. Since the probability of overloading is over 50%, the new capacity does not appear to be safe. Okay,